Okay, so our next speaker is Alex Schubnel from the ENS, so a local boy. And he's done some excellent work in the recent past looking at rupture properties in the lab, but also thinking about instability in very deep regions of the Earth too. And I think that's what you're going to be talking to us about today.
Yes, thank you very much, Dan. Thank you, Jan. Thank you, Barbara, for giving me the opportunity to present this work. So we're changing a little bit. We're staying in laboratory earthquake, but we're going much deeper into the Earth's interior. And this is a large research collaboration project that has been involving a number of people, and that has been largely funded by the ANR in the last years, and now we were lucky to be funded by the ERC. So the motivation is to understand the mechanics of those intermediate and deep earthquakes. So they have been known for almost 100 years now, since the first paper of Turner, and then obviously the papers of Wadati and Benioff. And if you look at the distribution of earthquake as a function of depths, this is in log scale, and as you see, most of the earthquake actually do happen in the first 50 kilometers or so, but beyond 50 kilometer depths in subduction zone environment, you still have seismicity, which decays exponentially with depths to reach a minimum around 400 kilometers. And once the slab entered the transition zone, so the zone where olivine transforms, you have an increased seismicity. You have this seismicity bump, which has to be linked in one way or another to the olivine phase transformation. And it has been long recognized that this exponential decay looks like an exhaustion mechanism. So there is something that makes the slab brittle that actually is getting exhausted as you go down, and one of the possibilities is the bringing water and hydrous minerals at depths. So there are some very clear observation of the role of slab hydration on intermediate depth seismicity, and there was a paper a few years ago by Shillington et al., where they looked at the Alaska Aleutian subduction zone, and they did two seismic profiles that I will show in the next slide along these two lines here, the so-called Shumagin gap and the Semidi segment. And just keep in mind that if you look at the Shumagin gap, you do have some intermediate depth seismicity around 200 kilometers, between 100 and 200 kilometer depths, whether along this path here, along the Semidi segment, there is no more intermediate depth seismicity. And if you look at the seismic profiles, this is the seismic profile along the Shumagin gap, and this is the refraction velocity model, where they see reduced upper mantle velocity. So basically, they argue that along the Shumagin gap, where you have the intermediate depth seismicity, the mantle is hydrated, whether here along the Semidi segment, there is little hydration. In any case, if the mantle is hydrated, it's very unlikely that it is fully hydrated all the way to the very deep, like let's say 50 or 100 kilometers below the mole. There is obvious evidence of deep focus earthquakes. There has been many, but in the last years, in 2013, we had the largest deep focus earthquake ever. This is the slip model by colleagues in America, where this is the maximum slip. So the earthquake happened is a magnitude 8.3. It happened at 620 kilometer depths. This is the Kamchatka Peninsula, and this is the Sakhalin Island. So we're around here. And interestingly, deep earthquakes generally don't produce lots of aftershocks. So that has been a long puzzling phenomenon. And in this case, only a few, half a dozen aftershocks are actually have been identified, with one triggered event here that happened on the same day, which is far enough to call it a triggered event, and it was very interesting because it's probably one of the first non-strike slip super shear earthquakes. So this earthquake actually did propagate around 8 kilometers per second. So the link between the olivine transformation and the deep focus seismicity has been questioned for many years. And one of the things is that because you do have earthquakes everywhere in the transition zone, if it was just the olivine transformation, you would think they would all happen at 400 kilometer depths, but this is not the case. They are actually happening over the entire transition zone. So in order to get that, you need to bring metastable olivine actually into the transition zone. So you need the slab to be cold enough to actually bring the metastable olivine wedge. And this has been discussed and imaged here in this paper of Kawakatsu and Yoshioka in 2012, where you see, or at least they see, a wedge of metastable olivine of reduced velocity entering the transition zone, and as you can see here, some associated seismicity. So the framework that was, well, or at least the people who were supporters of the mineral framework, let's say the mineral hypothesis, Harry Green, who unfortunately recently passed away, has put this cartoon together where basically one of the possibilities is that these lower Guadalquivir plain earthquake here at the intermediate depths are linked to serpentine dehydration. These ones we won't discuss so much, but probably to oceanic crust dehydration. And here in the transition zone, the earthquake would be generated by the olivine spinel transformation. And so there has been numerous experiments in the past, but none have really, until now, been able to couple at the same time the rheology and the laboratory earthquake proxy. So what we did here is we performed deformation experiments in order to investigate the mechanical role of mineral transformation. We did deformation experiments at in situ mental conditions. So we're talking about GPAs, pressure, and 1,000-degree temperature. So in conditions that are actually a bit extreme, in order to look at the rheological behavior of the rock when the transformation is happening under stress. So to do that, we took advantage of a revolutionary apparatus that has been developed in the last 15 years, which is the deformation dia, which is a multi-anvil apparatus. So it's a typical high-pressure physicist apparatus, except these two vertical anvils here are actually can be controlled separately. So you can actually bring the rock or your sample under pressure and then squeeze it. Because the sample is so small, you can't really measure anything ex situ. So what you have to do is to have this machine mounted on a synchrotron so that you're shooting X-ray through the sample and you're using X-ray to image the sample. And I will show you the role of the X-ray. So the first thing is that you use X-ray for radiography. So this is your sample. It's around 3 millimeter long and 2 millimeter diameter. And we put two gold foils on top and on other that are strain markers, and we measure the distance between those two gold foils. And that way we have the strain and the strain rate if we take this image every 2 minutes. And we also have the diffraction, X-ray diffraction. So the X-ray diffraction gives us an idea of the mineralogy. So all these rings are called Debye rings, and they are linked to the lattice spacing in the minerals. And so we know what minerals are in the sample. But also, if you look at these rings and you unwrap them, you see that actually instead of becoming lines, they look wiggly, because that's telling you that the HKL spacing or the lattice spacing is different along the different directions you're looking at. So if you know the elastic parameters of your material, you can fit those wiggles by sinusoids, and then you can extract sigma 1 and sigma 3. So you can extract the stress. And so from the X-ray diffraction, you have the stress and the reaction progress. From the X-ray radiography, you have the strain and strain rate. So now you're more or less into a regular rock mechanics experiment. And then behind each of those 6 anvils, here, we're putting acoustic emission transducer in order to listen to the sample. So basically, to hear if it cracks, basically, or to hear whether we have some small laboratory deep quakes. So I will show you two examples of what we've been doing in the last years. The first one on partially serpentinized peridotites, and the second one on olivine transformation. So in serpentinized peridotites, we've been working on hot pressed San Carlos olivine, which is the high pressure physicist olivine, to which we add 5, 10, 20, or 50% antigorite, which is the serpentine mineral. And we did experiment at a regular strain rate. This is the increase of temperature as a function of strain rate. So the temperature rate as a function of strain rate is around 1,000, so which is around comparable to what you would expect for a typical slab. And this is the stress strain curve obtained for samples at 1 GPa, where you have this is the stress measured as in olivine as a function of strain. And you see if you have pure olivine, it's very hard. And then as you increase the temperature, which is this gray hatch line here, as you increase the temperature, you see some temperature softening. Now you put 5%, 10 or 20%, 5% or 20% serpentine, you see that it's already much weaker. But at the moment you cross 500 degrees or somewhere here, basically you see that at least for the 5% starting material, you have around 40, you record around 40 acoustic emissions, so which are proxies for laboratory earthquakes, and I will come back to that. So if you do the same thing now at 3 GPa, well, you have the similar behavior, except now you have interestingly, I want to say that here we didn't have any acoustic emission for large amounts of serpentine, and I can discuss that in some details if you want. But in this case, we do see clearly the link between dehydration of serpentine, even for very limited amounts, so of 5 or 10%, or 5 or 20%, you see small laboratory earthquake being triggered. And we also see, and this we don't understand, some acoustic emission being triggered in pure olivine. So if you put that back on the PT diagram, this is the pressure, the stability diagram of antigorite here, ATG, as a function of pressure and temperature. And you see this green space is where serpentine is stable. And this is the path you would follow on the hot subduction zone. This is the path you would follow on the cold subduction zone. And this is the limit of the stability field. And the dehydration happens in 2 times. You have antigorite giving forsterite plus talc, and then forsterite plus enstatite plus water. And you see that at high pressure, we do see acoustic emission being triggered immediately when we have the dehydration, whether at low pressure, we seem to have acoustic emission being triggered only when we are at very high temperature. That is when we complete the dehydration. And this is linked, this is a technical issue, but this is linked, you see, that to the fact that here the Clapeyron slope of the reaction, so which is the limit here, has a negative slope. So the delta V, meaning the delta V is negative. So it means the delta V negative seems more likely to trigger acoustic emission. If you look at one particular acoustic emission, I'm sorry it looks really not so nice for you all seismologists, but this is the best we can do in a synchrotron environment. So this is a typical spectra. And we have, for the largest one, we have corner frequencies measured by hand like this, around a few megahertz. So that, for a rupture velocity of 4 kilometers per second, would give us something that is around 2 millimeters in size, and that's about the size of a sample. And so we can look if we find faults of 2 millimeters, and the answer is yes. So here it's one image of a sample where you can see here a fault trace. So this is 50 microns. You see the fault trace. If you zoom here on that, if you zoom here, you see it may be better. You see that there is an offset of around 10 microns. So we're talking about really magnitude -6 or -9 earthquake here. And if you zoom in this place, you see still the fault trace, and you see this little thing here that we will come back to, but later on. So I will show you, thank you very much, Giulio, for having introducing all the microscopy techniques. So I will show you now 2 fib sections. So this is 1 fib section, so in transmission electron microscopy taken here, and 1 taken across this little guy. And so the first one here, it's the green one. And if you look, this is the fault. It's hard to see, but the fault is here. It's very, very thin, on 100 nanometers. The fault length is 2 millimeter, but the fault width is 100 nanometer. And if you look in the fault, you see all these bubbles here, which are the dehydration products. So basically, in the fault, you see that the remnants of the serpentine dehydration. And in fact, if you do a diffraction close to the fault, what you see here in A4 is that you have amorphous material, but you also do have some nanocrystalline material, just like Giulio has shown in the calcite. But now we're talking about something that happened over a 10 micron slip only, but at very high pressure. So if you look now at the second fib section here, so the fib section is here. It's cross-cutting this thing that we call here an injectite. And in fact, if you look here, everything is amorphous. So we interpret this as a molten rock. And in fact, just next to this amorphous pocket, you do have euhedral, so like, really like with the crystallographic shaped olivine, nano-olivine here, that you see that grow like really in a very regular manner that really resemble olivine that would grow in a melt. So really, so you have the idea that in fact the fault plane must have melted during these very tiny earthquakes again. So we are talking 10 micron slip, and we were able to produce what Giulio at least would call the microbes of the tachylite. So this is here the typical triple junctions here of partially molten rocks, where the triple junctions are actually being how do you say, eaten. Here you see the corners are being eaten by the melt. Okay, so the interesting thing is that one of the conundrum is that it has generally been said that the serpentine dehydration would trigger dehydration embrittlement, and this dehydration embrittlement relies on a thing that the reaction produces water, and this water actually takes more space than the porosity that is created by the reaction. So basically, it's some sort of a hydrofracturation. However, this is only true, if you come back to the PT diagram, this is only true where the Clapeyron slope of the reaction is positive. This is not true anymore where the reaction is negative. Basically, when the Clapeyron slope of the reaction is negative, you produce water, but you produce more porosity than water. So technically, the pore pressure should drop and not go up. So that's the fact that we do see earthquakes in this region here tells us that the dehydration embrittlement model doesn't seem to work, at least in this condition, because we do. Thomas Ferrand came up with an alternate model, which we call the dehydration stress transfer model, basically where you have a framework of hard olivine where you have some patches of serpentine, and as you destabilize these patches of serpentine, you transfer stress on this big olivine asperity, and if you have enough dehydration, and then you will break the asperity, but the asperity also needs to be larger than the nucleation length, otherwise it will break seismically. So basically, you have 3 lengths here. You have the cluster length of the serpentine. Here you have the size of the olivine asperity, and here this would be the nucleation length. And in this little window where basically you have enough antigorite, but just enough, but not too much, so that the olivine asperity will be large enough and larger than the nucleation length, you will produce acoustic emission. So in the second part of the talk, I will come back on some now a bit old results, but that we've been revisiting on the transformation of olivine. And we did the experiments although at the beginning I said that we do everything at the right in situ mental condition, we're still not able to do it on the real olivine because the transformation would happen at 14 GPa, and we cannot go to 14 GPa with the acoustics, etc. So we do it on the germanium olivine, which has heat transformation at much lower pressure. And so this is the one experiment that we did on the pure magnesium germanate olivine. So we're at 4 GPa. The strain rate is 10 to the minus 4. This is the same differential stress now as a function of time. And in blue here you have the strain, and you see you have stress, you build up the stress, you're at 700 degrees and nothing happens, and by some sort of a very counterintuitive phenomenon happens when you increase the temperature. Any material, when you increase the temperature, you would expect it to become more ductile, and suddenly, as you increase the temperature by 200 degrees here, you have suddenly hundreds and hundreds of acoustic emission, and really the sample behaves as if it was pure glass. So initially what we just did, we looked at the large acoustic emission and the small acoustic emission, and we figured out that they followed the Gutenberg-Richter law, and we say, okay, it follows the Gutenberg-Richter law even on a small sample like this. So what you hear now is a sonification of those small laboratory earthquakes. But in fact, we were lucky that on one channel we did have a continuous record. So you hear some small ones, some big ones. So we have a variety of small and large laboratory deep quakes. Okay, and thank you, Ben Holtzman, for the sonification. And because I'm not a seismologist, our colleague from Chicago, so that was a big one. Our colleague from Chicago gave all the data to Lupe Zhu, who works at Illinois University, I think. And Lupe looked at the waveform and he said, but this is amazing because all your acoustic emission looked exactly the same. So you see, and he figured out that we have thousands of them, but he figured out that they all were in 2 different groups. So this is our 6 channels, and you see that they really look like almost like repeaters, but obviously everything looks like a repeater when your sample is a millimeter square, millimeter cube. And so he applied, for the first thing he did is he applied the double difference technique to relocate the earthquake. And we also have the tomographic images. So this is here the sample after deformation where you see the 2 faults, and you actually see the relocated faults. I want to say that this is 2 millimeters, so we have a resolution that I never thought would be ever possible, because we really seem to be able to track these faults with our acoustic emission. So the second thing he said, well, since we have one continuous record, we can do template matching. And so he took one event and he basically reread the continuous waveform. And once he did that, this is our initial histogram of magnitude distribution that I showed with the b-value that we initially measured here, and that he remeasured better with a different number. He was able to get many thousands more of events, especially very small ones, and we get a different b-value. But now we have enough events that we can look at the temporal series during the experiment. And if you do so, this is the time as a function of distance. So you see the events and on the fault 1 and fault 2. You maybe see some migration here, actually. But I think what you see clearly is that at the beginning you have small events and you tend to get larger events later on. And if you look at the evolution of the b-value during the experiment, this is the black line here, and you see that at the peak of seismicity, so basically when the sample breaks, we do have a minimum in b-value and a peak of seismicity. So it's telling you that this small olivine sample prepared its failure at high pressure. So you do have a nucleation phase. Even in, obviously you have to have a nucleation phase, but here it's very obviously shown. So what Loupé did also was to measure, to do the focal mechanism inversion, actually not focal, the moment tensor inversion. And so he measured the isotropic and shear component. And most of the events have a very small isotropic component, let's say around 0, or between 0.1 and minus 0.1 and 0.1. And we have a very large possible CLVD component where we go from minus 0.5 to 0.5. So our events are still in shear. So this is also something that they share with the real deep focus earthquake. So if you look at the sample now, I will show you just to finish a bit of microstructure. So this is the main fault. But before zooming on this main fault, we're going to zoom somewhere here. Up. And this is a set of conjugate faults in the samples where you see here small pyroxene grains being sheared. You can all see the sense of shear, etc. But our understanding is that those events that have large CLVD components might actually come from not from single fracture propagating in a single way, but by many fractures actually propagating in together. So it's very hard to imagine, at least to me, that you had this fracture propagating, then this fracture propagating, then this fracture propagating. I would rather have an idea of like all the fractures propagating together and the system collapsing like a little bit like a deck of cards that you're pushing and all the cards moving together. And this could be the origin of the large CLVD component. So we see this about everywhere in the sample. This is another example where we see those very nice parallel features. I want to say that there are some evidence for intermediate and deep earthquake when people do back projection, where they see two focus propagating almost together, two foci, sorry, propagating almost together in the. So maybe that our idea that faults, that an earthquake is just one single fault propagating in this condition might not be the case. You might have several faults propagating at the same time, which could explain the CLVD, the large CLVD component we see. So if you zoom now at on the main fault, we're going to zoom here at somewhere where it's still sealed, and this is what we see. You see again a grain of pyroxene. This is the other part of it, and the grain has been sheared around 30 microns. So now you have a main fault on which the displacement is 30 micron, and we can zoom in front of it, and you see that the fault is marked here, but as earlier on, the faults are marked always marked by very thin white or lighter gray material. This is an image that is taken in backscattered mode. So basically what you're looking is the density contrast, and the lighter, the denser the material is. So basically this is just telling you that this material, which is inside the fault, is actually denser than the surrounding material. I think you can see where I'm going to. So we do a fib section along one of those lines. And if you do a fib section along one of those lines, this is one olivine grain with some slip bands here and a large amount of dislocation. This is another olivine grain, and this is the fault. Now the fault is 100 nanometer across, and you see that the fault is made with this very fine grain here, and if you do the XRD on this grain, it is actually compatible at least with the spinel face, and we know there is the spinel face. So basically it's as if the fault was filled with the high pressure olivine. So inside the fault gouge is the high pressure olivine. So, and if you look at very detailed, now this scale is 2 nanometer, a bit like in the images of Giulio. Now here you see, and it's always amazing to me, that here this is actually the atoms being well lined up. So this is the lattice plane of the olivine, actually not of the olivine, of the germanium ringwoodite. And this is another grain, and you see that it is fully crystalline. We can't find any melt in this system. So there is something that we don't understand. In one case, we were at lower pressure, we break, we melt, and here we are at higher pressure, we break, we have larger slip, and we don't melt. So obviously, there is something that is going on. And just to finish and discuss is just to say that we have, I mean, these experiments tell us that we have been so much, we have this vision in our mind of the energy balance of the earthquake, of the earthquake fault, where you have the fracture energy, the radiated energy, and the heat. And it's not that I don't think that this balance is wrong. I just think that we always think that the fault plane actually doesn't contribute to the energy balance. And in fact, minerals have enormous amount of potential heat in them because they transform, and the transformation can be endothermic or exothermic. And they also have an amount of work in them because they can produce fluids or produce porosity, so they can reduce the pressure or increase the pressure. And so we need to try to find a way to incorporate this in our energy budget, because obviously it's not a nil process. And just for you to see, so in the case of the olivine alpha gamma transformation, the latent heat, so it's exothermic, and the latent heat is around half a terajoule per meter cube. So if you transform 1 meter cube of olivine into its gamma phase, it will produce half a gigawatt of heat. And the fracture energy of the Tohoku earthquake is around 30 to 60 megajoule per meter square. So basically there is in 10 centimeter of olivine transforming into spinel, there is as much heat as like the 1 square meter of Japan sliding 50 meters. Okay, so just to tell you that those energies are not to be neglected. So to conclude, well, I think I showed you that we do reproduce intermediate depths and deep focus earthquake analogs. We did some similar experiments on eclogitization of both the continental crust and the oceanic crust, and we do see, again, acoustic emission triggered in one case by the glaucophene breakdown into amphasite, or in dry granulite by the plagioclase breakdown. And there are some very new results now where people have been looking at the enstatite to high-pressure clinopyroxene phase transformation, which is also has the same, is a positive Clapeyron slope and exothermic. And this should happen around 200 to 300 kilometer depths, and that transformation could very well explain some of those weird earthquake nets that are found in some places on Earth at 200, 300 kilometer depths. So just to finish, I think I'm pleading at least that seismologists should not neglect minerals. Okay, thank you very much.